Hi, my name is Rolf Agner, and welcome to On Air with SICK, where we discuss insights from industry experts on autonomous mobile robots, or AMRs, in the material handling industry. Today on our show, I am joined by Alex Wyglinski, Electrical and Computer Engineering Professor at Worcester Polytechnic Institute in Massachusetts. Alex and I discussed how mobile robots are impacting academic research and how students are embracing this technology. I hope you enjoy our conversation. So Alex, how have mobile robots impacted academic research and the educational curriculum?
The area of robotics is very interdisciplinary and involves a lot of moving parts. A little bit of a pun. But the idea is that you have these systems that require knowledge, not just in one area, but from multiple areas in order to sort of figure out in its entirety how a platform works. So like a robot, whether it's a ground-based robot, an aerial robot, could even be an autonomous vehicle. And as a result, in education, this makes for a very interesting and very powerful tool. First of all, it's very visual. It captures the imagination. So you have students all the way into like elementary school getting engaged with this technology. They see it, they put it together, it does an action, and instantly it gets students hooked. It's sort of saying, wow, what's making this all move?
But it's fascinating for them. When I grew up, we had a Rector set, American bricks, and Lincoln logs. Hope that doesn't date me, but quite a more intriguing, more inviting, more stimulating environment today.
Exactly. Well, nowadays, like you have things like Lego Mindstorm as an example, and there are a lot of like do-it-yourself type of kits out there. And what ends up happening is that this gets young people sort of engaged with this concept of robotics and automation. And then we have this sort of flurry of different types of robotics competitions out there, including the really well-known one, which is FIRST Robotics. So students then join robotics clubs in high school. And then when they come into college, even in high school, but when they get into college, they begin experiencing programs that more formally teach the fundamentals, the individual components that allow for a better insight on precisely how these robotic platforms work, what are their limitations, and what they're capable of. So for instance, at WPI, we have a really well-established robotics undergraduate program. It's one of our most popular programs. It attracts students from all around the country and around the world. And this program really pulls from concepts from electrical and computer engineering. That's kind of my core academic profession. I'm an electrical and computer engineer, but it also pulls knowledge from mechanical engineering and from computer science and brings them together in order for these students to sort of say, okay, I'm going to make this robot that follows perhaps like colored markers on the ground in order to track, say, some sort of obstacle course in order to get to some desired target destination. And what ends up happening is these students, they begin appreciating things like, for instance, there's mechanical aspects of these robots. They need to understand things like, for instance, weight. They need to understand factors such as like mobility, perhaps even things like in under ideal circumstances, robots might not weigh anything and might move instantly. But in the real world, you have things like friction. So what ends up happening is that with robotics and mechanical engineering aspects, things like, for instance, mobility, like weight, very importantly, even things like the structure of the robot itself. Like, for instance, like the strength of the materials themselves. Suppose you want to create a robot that lives 100-pound weight. Oh, and I'm going to do it all together with just like tongue compressors and matchsticks and stuff. Well, that might be difficult. Even like 3D printed components and such, that might actually be very difficult to pull off if the 3D printed materials are not rated to lift that type of mass, right?
Sure.
From a computer science perspective, it's coding. How do you code this to be computationally efficient, especially if it's on a limited limited platform, such as like perhaps it's like a Raspberry Pi. You won't be able to run tons of code on a Raspberry Pi or Arduino or some sort of like platform that has limited computational complexity. So you get an appreciation of platform with limited computational horsepower, and you got to think smart. You got to think, okay, how do I make all these really sophisticated maneuvers, right, and all this data processing, but I have limited computational horsepower. And then from the electrical and computer engineering side, there is also the fact of this embedded computing with the computational horsepower. That's a major factor, but there's also things like sensors. So that is a really important part of robotics. It's knowing your environment. It's that situational awareness. It's understanding what's around you, sensing it accurately, sensing it from multiple devices, feeding it into that embedded processor, being analyzed by that algorithm, and then being translated into action. And then that action being relayed to, let's say, a motor or whatever sort of device in order to perform some sort of corresponding maneuver, some sort of action. So what ends up happening is you have all these different disciplines all playing together. And I think people get, these young people, they sort of get introduced to it very early on, like in elementary school and high school, but they don't know what the fundamental concepts are. And then in university, they begin to pick up on the fundamentals in a very deep and detailed way, and start to hone their skills as robotics engineers, as experts in automation, and begin to specialize in terms of really understanding what the limitations are of this technology is, as well as pushing those limits to really do advanced operations using robots.
I could imagine that many of the students are somewhat awed at this point. They see the system, the robot systems, the mobile vehicle system, and they get a general perspective. But then when you start zeroing in on the individual components it takes to make that system, they find that there's a lot of specialty and there's a lot to learn in those areas. And trying to make a decision on whether you stay generalized or your interest in a certain area become more focused is what can be going through many people's minds, I imagine.
Well, yeah, I think at the beginning, what's kind of interesting is, like, for instance, our robotics engineering program, which as of earlier this year now became, a full-blown department. So now we have a department of robotics engineering that awards bachelors of science in robotics engineering. The Bachelor of Science in Robotics Engineering, actually, we've been doing it for quite a while, but the fact that now it's a fully fledged department of robotics engineering, well, this is great for the university. But what ends up happening is we attract students that are all interested in robotics engineering, and there's a certain angle, there's a certain aspect of robotics engineering that these students really are attracted to, whether it's the computer science side with the coding, whether it's the mechanical engineering side with the actual structure of the robot, its weight, its structural integrity, its strength, and then finally the electrical and computer engineering side, which is the embedded computing, which is the sensor side and the actuation side. You really see this from the students when they come in. Each of them kind of like, they all are interested in robotics, but I think some of them really kind of declare earlier on what preference they have. So it's really cool seeing that. And it's approximately a third.
Our company makes LiDAR products and vision products. Are they exposed to any of these type of concept at this stage?
Yes. So in fact, so WPI is very active in terms of project-based learning. Like that's at the core of our educational mission. It's project-based learning. Whatever we teach in class, they also learn in projects and hands-on activities and stuff like experiments and labs. LiDAR, very much so. very much so. So personally, I've advised 3 projects in the last several years that have used LiDAR products, LiDAR sensors, in order to demonstrate a proof of concept, right? So what were they? So one project used the LiDAR in order to detect the presence of people that potentially could be in a dangerous position when one of these large city buses actually make a wide turn. So that turns out actually to be a major source of injury and even fatality whenever there is an accident with a city bus, right? Like, so you have one of those really long, 48-foot long buses. They're turning at an intersection. What turns out is that there's a very large blind spot in the midsection on the outside of those buses. So when they make that turn, they make a big sweep. And if there's somebody in that blind spot, that's a really dangerous place to be, because the driver is unable to detect the presence of that pedestrian outside. So I had a project that did a proof of concept using LiDAR in order to detect the presence of humans in those blind spots and alert the driver. So that's one project. Another project involved using LiDAR in order to make a proof of concept autonomous Baja racer vehicle. And again, that LiDAR was critical in order to do things like motion and path planning of that vehicle through a complicated obstacle course. So again, like, LiDAR is beautiful there because you have a point cloud that allows you to kind of really tell you what does the landscape look like and translate it from the physical world to the computer world, where then that information gets processed and gets translated into action, like how that vehicle should drive that obstacle course. And then lastly, earlier this year, I had a team of students compete in the SICK competition using a SICK LiDAR in order to detect the presence of potholes. And that was also a great proof of concept, because that was able to take the physical world, in this case, the surface of a road, identify the presence of potholes, and translate that into an actual action, which is, in this case, a mapping saying, here's a pothole, here's a pothole, here's a pothole. So instead of visually inspecting using a human, you actually have a LiDAR unit be able to identify the presence. So that WPI team, in fact, won first prize in that competition.
We have some experience at SICK in applications similar to some of those, and we've also, in addition to LiDAR, have used our 3D vision products. In fact, for looking for potholes and examining railroad ties and the stone around railroad ties and plates and spikes and that kind of thing. Those are real world applications that this type of technology, both the LiDAR and the 3D vision products are using.
Yeah, like in electrical and computer engineering in particular, I always say to a lot of folks, this generation of electrical and computer engineers are really at the forefront of something called cyber-physical systems. So you have the physical world, like the railroad ties, like the street conditions with the potholes, like the obstacle course for an autonomous vehicle. And you need to translate that into the cyber world for the computer algorithms to understand what's going on and to process that data, like, big data, data science, and then translate it into action, right? And then that action then gets converted back into the physical world, into motors turning, into wheels turning, and such. And so that sensor connection between the physical world and the cyber world, like that boundary where those sensors come in, like LiDAR units and such, that's where, like, in particular, the electrical and computer engineers play right now. So it's great. And in fact, that's really neat about railroad ties and understanding their health. And this also applies to a much broader world, translating the physical world into that cyber world. It's quite necessary. We live in a world that more and more that boundary is applying to a lot of different applications.
Yeah, and we are definitely seeing the integration of these, what used to be separate technologies, put together to give you all that additional data you need to analyze and make these decisions.
Exactly.
So what are graduates doing after graduation? Or are there advanced programs available, advanced degrees in this? We talked a little bit about early on what they're doing, but tell me more about what happens, let's say they get their degree.
So for the WPI student in general, we have a really good place, like I would say an excellent placement rate in terms of having our graduates be lined up often with their first choice companies across a wide range of disciplines and like activities and foci. Like, so for instance, robotics engineers in particular, there is a critical mass of robotics engineering companies located here in the Massachusetts area. Electrical engineering, absolutely. Like, I think our placement rate within our university alone is one of the highest. We're nearly 100% placement.
Wow.
Our students often go to everything from sort of brand name robotics companies, for instance. A lot of them go to companies that focus on things like sensor technologies, like defense contractors. Quite a few also go on to graduate studies that like they get bitten by the bug in terms of understanding, oh, this is really neat how like for instance, these sensor technologies and the CyberPhysical Systems, how this all is. But I would like to know even more. And they go into everything from, for instance, there's a robotics engineering master's program and PhD program. Sometimes a lot of these students, they want to specialize specifically in something like an electrical and computer engineering master's and PhD program, or a computer science master's or PhD program, or a mechanical engineering master's or PhD program. Sometimes they even branch off into something that's not even like, really described at the undergrad level, but there's hints and suggestions that are made, but then, oh, holy smokes, there's actually an entire graduate program in it. Like, for instance, we have a really well-established master's and PhD program in systems engineering, which in many ways describes robotics engineering at a whole new level.
Sure.
And we have a really well-established, comprehensive systems engineering graduate program at both the master's and the PhD level. We also have like master's programs in our business school, like both MBA as well as in terms of like engineering technology and the like understanding like how do you now have like these complex systems? How do you work in teams to more efficiently try to tackle these really complex engineering problems? In general, we have our students branch off, either they go directly into industry, and really our students are really sought after given their expertise in things like robotics engineering, like electrical and computer engineering, like computer science and mechanical engineering. Quite a few of them go into advanced degrees and like master's and PhD studies. Some of them also go into the service, like through our ROTC programs that we have here at WPI. And with this background, these are really, really sought after programs because more and more our world is becoming roboticized, is becoming automated, is very much a smart world, is very much a cyber-physical world. Like, and it's exciting. It's not only at WPI, although I like to think that WPI is at the forefront of institutions that are really helping our students develop professionally into these professions.
Let me ask you this. Have you seen any evidence of maybe a couple of students getting a concept, an idea while in school, but upon graduation or moving on, they get together and further develop that as a startup company or something of that form?
Very much. Yes. There's definitely a lot of activity. Like, that's another element at WPI. We really promote entrepreneurship. So that project-based learning, that hands-on learning, in hand with that, like plus the fundamentals we teach, plus sort of the number of programs we have, especially related to automation, to cyber-physical systems, to robotics. There is definitely a culture here of entrepreneurship, and a lot of our students usually run with it. If they create a really cool product, our school really helps in terms of preparing our students with, if they have a good idea, with trying to turn that into something that could potentially turn into a startup venture, or find companies that can work with our students in order to make it a product. Absolutely.
Fantastic. Now, are they generally sticking to the New England area where you're located, or do you see them venturing out in different parts of the country or the world?
Well, our students, when they graduate, quite a few of them stay local, but also a number of them find fantastic opportunities in places like Silicon Valley, in places like Austin, Texas, which is like another Silicon Valley,
sure,
and definitely opportunities around the world. Like our students are very much sought after, not only locally but from around the world. And also our school, additionally, when we talk about project-based learning, we also have a very significant global education reach, if you will. A lot of our project-based experiences do happen globally. So we have a senior design capstone experience, which we call a major qualifying project, or MQP. But we also have something called an interactive qualifying project, or IQP, that's done in the junior year, and it really kind of focuses on the sort of socioeconomic, technological perspective of trying to solve problems that maybe they don't have like a deep sort of technical aspect. It's not like a senior design capstone project, but it's more like, let's understand this problem better and then come up with potential solutions that can eventually turn into a product that can help, let's say, make the quality of life better for a specific community. Like, for instance, how do you perform, let's say, irrigation for a community in a developing part of the world using off-the-shelf components that can be done economically, right? Without breaking the bank, without so there's ways of bringing water to a farm, but then there's economic and practical ways of irrigation as well. And that's where our students learn. And I would say a good chunk of our student population, undergraduate student population, go off campus in order to pursue those projects.
The other thing that I was wondering about listening to you was, what about students that go out in the field?
Yep.
They go to a company, they start their own company. Do any of them come back for further courses or further education?
Yes, I definitely think so. Like I have a few academic advisees. What they've done is, as they're trying to, a few students, what they do is they go out and work in the industry for a few years, and then that idea that they have obtained, they work it on the side, and then when they feel the idea is matured enough, they start their startup venture, right? And then you have some students that jump right away into it, and they also take graduate courses, graduate degrees. Maybe it's in electrical and computer engineering, maybe it's robotics engineering, but also maybe we also have a master's in things like entrepreneurship, right? And so we do have our students, because of the flexibility of the program, and our students really do jump into things like these new topics, new ideas, and try and see if they can make a go of it. Sometimes what they do is they might say, oh, I want to work for a few years and see how a company works. How does it work in terms of project management? Kind of get their feet wet in terms of what is life like after school? What's life like in industry? And then they come back to the idea, and then they begin to grow it, and then ultimately venture out into the startup world. Some jump in right away, and I've seen a few of those and are quite successful. And then some do that while they continue with graduate studies.
I can see the disciplines they get into depending upon what their interests are, what stimulated them. For example, I had a childhood friend, very, very intelligent person, went to college and without even getting a degree was put into a graduate program and ended up with a PhD in mathematics. So you can just imagine how intelligent. He ended up having a great career with General Motors Company. However, when he retired, guess what he did? He went back to school. Went back to get an undergraduate degree in business and eventually an MBA because he felt that he was unfulfilled and had some ideas, entrepreneurial ideas. In order to really develop them, he needed these skills. He went back and did it.
That's exactly.
And then I had another friend, actually a colleague in college, taking engineering courses. This was a person that worked in actually designing highways. He worked for a consultant that designed highways. And he found he needed more mathematics because they were doing a lot of logistical studies on population movement and expansion and contraction. And he found that he needed additional mathematics and engineering skills, systems engineering, in order to design more efficient highways. And that just fascinated me.
No, that's so cool. Actually, Rolf, I've got to drop off, but